Hello everyone and welcome back to Math 143, Finite Mathematics. In our previous lecture, we learned how to graph systems of linear inequalities and identify feasible regions. Today, we will use those ideas to solve linear programming problems. Okay, linear programming. What is the linear programming problem means? So the linear programming helps businesses answer this questions such as how can we maximize the profit? How can we minimize the cost? How should limited resources be allocated? So these type of questions arise in manufacturing, transportation, finance, scheduling and many other real world applications. So by the end of today's lecture, you should be able to define an objective function, distinguish between maximization and minimization problem, write constraints from a word problem, graph the feasible region, find the corner points of the feasible region, and determine the optimal solution for the linear programming problem. Okay, let's begin with the basic idea. So, what is linear programming? What is linear programming? So, suppose you own a company that makes two products. Suppose you own a company that makes two products. Right? So, you have limited resources such as labor, materials and time. Also, you have limited resources such as labor, materials and time. Okay. So, you want to decide how many units, how many products of each product to produce to earn the highest possible profit. So, then you want to decide how many units of each product to produce to earn the highest possible profit. Okay. So this is exactly what linear programming helps us to do. So a linear programming problem always has three major parts. So an objective function, a set of constraints and non-negativity restriction. So the linear programming problem help us to identify what? The objective function or what we wanted to optimize. Okay, let's say this is exactly what linear function or linear programming helps us do. So, first of all, a linear programming problem always has three main parts. The first one, an objective function. Second, a set of constraints. Third, non-negativity restriction. So the non-negativity restriction meaning our variables cannot be negative. Okay, let's start with an objective function. So, an objective function or the objective function tells us what we want to optimize. The objective function tells us what we want to optimize. So there are two possibilities. The first one is maximization. First one, maximization. What are the examples? So let's say maximum profit, maximum production, maximum efficiency. So examples are maximum profit, maximum production, maximum efficiency, okay, next. The second one is minimization. So, for an example, minimum cost. We wanted to minimize the production cost. Also, we wanted to minimize the travel distance. Also, we wanted to minimize the time for the production. So, minimum time. Those are the examples. So, a typical objective function. So, let's see the form of the typical objective function. A typical objective function has the form z equals ax plus by, where x and y represent the decision variables, where x and y represent decision variables, a and b are constant, z, see what we want to optimize, right? What we want to optimize. Okay, then let's see the quick example. For a quick example, suppose each table earns $40. and each chair earns $30. So what should be the objective function, or what should the objective function be? So let's say let x be the number of tables and y be the number of chairs. So per chair we can earn $30. Per table we can earn $40. So that means we wanted to maximize the profit earned from x number of tables and y number of chairs. So z equals 40 times x plus 30 times y. The objective function does not tell us how many products we can make. It only tells us how we measure the success, right? So maximize profit. So this should be the profit function and maximization problem. So the objective function does not tell us how many products we can make. It only tells us how we measure the success. Okay. For every linear programming problem, we will follow the same 5-step procedure. So let's see the 5-step procedure. So the 5-step process. Step 1, define the variables. So for an example, x number of tables, y number of chairs. According to the given word problem, define the variables. Step 2, write the objective function. Write the objective function. Step 3, write the constraints. Step 4, graph the constraints and identify the feasible region. Step 5, evaluate the objective function at every corner point of the feasible region. So this process works for every linear programming problem in this course. I hope you remember the feasible region. The feasible region is the region where the all constraints, all inequalities satisfied. Okay, let's go through the note. Here you can see the objective function and the linear programming problems, also the examples. Okay, let's start with the maximization problem. Okay, so in that case, you can read the word problem. A division of Penny Mustard Furnishing in Milwaukee manufactures dining tables and chairs. Each table requires 40 board feet. Each table requires 40 board feet of wood and 3 labor hours. And each chair requires 16 board feet of wood and 4 labor hours. The profit for each table is $45 and profit for each chair is $20. In a certain week, the company has 3,200 board feet of wood and 520 labor hours available. How many tables? So the question asks, how many tables and chairs would Penny Mustard manufactures to maximize its profit? Okay, then read the problem slowly and identify the required information. Okay. Okay. Let's see. Suppose, so the question says, suppose a furniture company manufactures tables and chairs, right? Okay, each table requires 40 board feet of wood, also 3 labor hours, and each chair requires 16 board feet of wood, also 4 labor hours. The company has available 3,200 board feet of wood and 520 labor hours. Available. Right? Then the profit is from chair per chair $20, per table $45. Okay, those are the required information. So then let's follow the 5-step procedure to solve this linear programming problem. Okay, step 1, define variables. Think about what are the variables? We have 2 products, tables and chairs, but we don't know how many tables, how many chairs. Therefore, the variables should be X, number of tables, Y, number of chairs. So let X be the number of tables, Y be the number of chairs. Second, step 2, define the objective function. Okay, to define the objective function, I would encourage you to do the two-way table because we have the given information here. Let's say tables and chairs. Table and chairs. Also, what are the things? Board feet and labor hours. Also, profit and availability. Right? For each table, we need 40 board feet of wood and 3 labor hours. 40 board feet and 3 labor hours. And the profit from table, $45. For chair, 16 board feet, 4 labor hours, profit 20. 16 board feet, 4 labor hours, 20 profit. And the total availability of board feet 3,200 and the labor hours 520. $3,200 and 520, right? Okay. Okay, then let's define the objective function. The objective function should be the profit function. So this, let's say C, profit function C, from each table $45, earn $45 and number of tables X. And from each chair $20 and number of chairs Y. So we can write down the objective function. The objective function 45x plus 20y. Since we produce the x number of tables and y number of chairs and per table $45, per chair $20, the total profit would be 45 times number of tables plus 20 times number of chairs. Okay, so are we maximizing or minimizing? Maximizing. Profit. Okay, step 3, write down the constraints. So, step 3, constraints. So, the easiest way to write down the constraints is use this two-way table. So, the first row of the two-way table, it defines all the available board feet and board feet per table and chairs. So, using the two types of available materials here, board feet and labor, we can write down the two inequalities, two constraints. So, let's see the first row of the table. So it says what? 40 board feet per table, 16 board feet per chair and total availability 3,200. So now we know the number of tables and chairs. Therefore, the total from the wood, we can write the total number of board feet to produce X tables plus total number of board feet to produce Y chairs definitely less than or equal 3200 because the available board feet are 3200. The first constraint 40x plus 16y less than or equal 3200. Second, for labor hours, the second row of the table. 3 labor hours per table, 4 labor hours per chair, and total available 520. So X and Y, the number of tables and chairs. Right? Okay, then let's see. 3x plus 4y less than or equal 520. Okay, what about the others? So, I hope you remember that the non-negativity that means the number of chairs we produce and number of tables we produce cannot be negative. So the wood available tells us it cannot exceed the 3200 available value. The labor hours says it cannot be exceed the available labor hours 520. Also, we know that the number of table and number of chairs cannot be 0. Therefore, the non-negativity constraints, all the available variables are non-negative. Okay, I hope everything clear so far. Then, let's move towards. Okay, so step number 4. The next step. What should be the next step? Graph the constraints. Graph the constraints. Okay, let's graph the constraints. Step 4. Graph the constraints. There are 4 constraints. We can say that 40x plus 16y less than or equal 3200. So we can simplify this. So let's simplify this up to, we can divide each term by 8. So 5x plus 2y less than or equal 400. So let's draw the graph. First, 5x plus 2y less than or equal 400. We know that to draw the inequality, first we want to find the boundary line. The boundary line should be the equation. Boundary line. Also solid boundary line because the equality sign is here. Then when x equals 0, 2y equals 400, y equals 200. When y equals 0, 5x equals 400, x equals 80. Right? So the points are 0, 200, 80, 0. Okay, let's go through the second one. Let's go through the second one. 3x plus 4y less than or equal 520. 3x plus 4y less than or equal 520. When x equals 0, 4y equals 520. So 520 divided by 4, 130. When y equals 0, what happened? 3x equals 520. X equals 173.33. So the points are 0, 130 and 173.33 and 0. Also, two other constraints. X greater than 0. This gives us x equals 0, y-axis. Y greater than or equals 0. This gives us y equals 0, x-axis. Okay, then let's draw the graph. So to draw the graph, first we wanted to draw x, y, 0, let's say 50, 100, 150, 200, 250 and negative 50. So let's say 50, 100, 150, 200, 250, 300, negative 50, negative 100, so negative 100. Okay, let's draw the first inequality. So it passes through the point 0, 280, 0, 0, 280, 0. A solid line, right? A solid line. And the solution region for the first constraint would be 0, 0 included, because when we plug the 0, it should be less than 400. So below the line, right? Okay. Then second one, 0, 130, 0, 130 and 173, 0. Here again a solid line, and below the line, so the solution region from the second line would be this. Okay, this is the line 3x. This is the line 3x plus 4y equals 520. This is the line 5x plus 2y equals 400. Okay, next. X equals 0, that is the y-axis. Y-axis. And it says greater than. Therefore, all x values are greater than the plane here, right? Greater than. Next, it says y equals 0, that means x-axis. X-axis. And y greater than 0, right? Y greater than 0, x greater than 0. So the y greater than 0 means this. Okay, then let's find the feasible region. The feasible region is where all four regions are satisfied. So we know that all four regions are satisfied within where? So all cross points are here, right? All four regions are satisfied in here. So this would be the feasible region. Feasible region. Okay, now we find out the overlapping region, so that is the feasible region. Then next, corner points. Step 5, find out the corner points. Okay, what are the corner points? For the feasible region, we can see that this is the corner point, this is the corner point, this would be the corner point, also this is the corner point, right? So with 4 corner points, we know this one, that is the 0, 0. We know this one, this is 0, 1, 30, and we know this one, that is what? 80, 0. And we wanted to find out this. We wanted to find out this. Okay, then how to find that point? So I hope you remember that. Here is the point that intersect what? It intersect the two lines, the two constraints, 5x plus 2y equals 400 and 3x plus 4y equals 520. So that means we should find out the intersection point. So intersection Okay, then let's find the intersection point. So the intersection point of 5x plus 2y equals 400 and 3x plus 4y equals 520. Equation 1, equation 2. So it is easy to multiply that 1 by 2 minus 2 to remove the 4y. 5x times 2 multiplication by 2, each term we should multiply each term by 2 minus 3x plus 4y, 2 times 400 minus 520, then 10x plus 4y minus 3x minus 4y equals 800 minus 520. So we can cancel this out, then 7x remaining in the left side, then right side 800 minus 520, 280, then divide by 7, x equals 40. X equals 40. So substitute in x equals 40 into the either of 1 or 2. So let's use 5 times x plus 2y equals 400. 5 times 40 plus 2y equals 400. 200 plus 2y equals 400. 2y equals 200. Y equals 100. Right? So the intersection point is 40 and 100. Okay, now we all know the 4 corner points. Then let's evaluate the objective function. with every corner point. Okay, we have the objective function. Step 5, continue. Evaluate the objective function for every corner point. Okay, so let's construct. We have z equals the objective function z equals 45x plus 20y okay, that would be the profit function. So we have corner points 0, 0, 0, 130 and 80, 0 and 40, 100. That is the intersection. Okay, let's evaluate the profit. So when x equals 0 plus y equals 0, the profit equals 0. When x equals 0 plus y equals 130, 2600. When x equals 80, 20 times 0 because y equals 3600. When x equals 40 plus 20 times 100, what happened? This is 1800, this is 2000, 3800. So whichever value is the largest, that is the optimal solution. So the optimal solution is 3800, which occurs at the corner point 40 and 100. So that is the optimal solution. The optimal solution is $3,800 at x equals 40 and y equals 100. So we can say that the maximum profit of $3,800 can earn by producing 40 tables and 100 chairs, because x is tables, y is chairs. Okay, you got it. Okay, one additional example. Try it by yourself. Suppose we wanted to maximize z 5x plus 8y. The given corner points are 0, 0, 0, 10, 64 and 80. Compute the objective function and identify the maximum. Okay, pause the video and try it by yourself. Okay, next. Not every businesses want to maximize in something. Sometimes we want to minimize the cost. So let's see the minimization problem as an example. So this problem, the word problem here, Foxworld Travel has decided to advertise in 2 major newspapers in a major city. These advertisements are directed at 3 groups of potential customers. Each advertisement in newspaper 1 is seen by 7,000 group A customers, 40,000 group B customers and 20,000 group C customers. Right? Also, each advertisement in newspaper 2 is seen by 10,000 group A customers, 20,000 group B customers and 40,000 group C customers. Okay, each advertisement in newspaper 1 cost $1,000 and each advertisement in newspaper 2 cost $800. Foxworld would like their advertisement to be read by at least 2 million people from Group A, 1.4 million people from Group B, and 1 million people from Group C. How many advertisements should Foxworld place in each newspaper to achieve its advertising goals at a minimum cost? Okay, step 1. What are the important things and define the variables? So first identify the important things here. So you can see that there are 2 newspapers, newspaper 1 and newspaper 2, right? Also, you can see that group A customers for each newspaper. Group B customers. Also, Group C customers and Group C customers, right? And we can see that, so newspaper 1 cost 1,000 per advertisement, newspaper 2 cost 800 per advertisement, right? And their requirement, you can see that Foxworld would like their advertisement to be read by 2 million people from Group A, 1.4 from Group B, 1 million from Group C. Okay, those are the important information. Then let's define the variables. So, when we define the variable, step 1, let X be the number of advertisements in newspaper 1, right? And Y be the number of advertisements on newspaper 2. Okay, then let's define the objective function. Before that, complete the given two-way table. Okay, let's define the values. So for a newspaper 1, group A 7,000, group B 40,000, group C 20,000. 70,000, 40,000 and 20,000. Newspaper 2, group A 10,000, group B 20,000 and group C 40,000. And the goal is 2 million for A, 1.4 million for B, 1 million for C. 2 million, 2 million, 1.4 million and 1 million, right? Then finally the cost, we want to minimize the cost. For a group A 1,000 and newspaper 1 1,000, newspaper 2 2,000. Okay, let's define the objective function then. So using the last row here, we can easily define the objective function. We wanted to minimize the cost 1,000 x and 2,000, sorry, 800, right? Yeah, I did wrong. You wanted to catch me up. Here it should be 800. $800y, the cost. It's a minimization problem. Right, okay. Then write the constraints. Step 3, the first row of the table, second row and third row. Okay, let's quickly write it down. 7,000 x plus 10,000 y greater than or at least 2 million, right? It can be greater than 2 million also. And the second one, 40,000 x plus 20,000 y greater than or equal 1.4 million. Third one, for the group C, 20,000, 40,000 greater than or equal 1 million. Because whenever the problem says at least, we use greater than or equal. Whenever it says at most or available, we use less than or equal. Note whenever the problem says at least, we use greater than or equal. Whenever the problem says at most or available, we use less than or equal, right? Okay, so within the constraints we can see the large numbers, right? So let's simplify the values. So we can easily simplify them by dividing the 10,000 by dividing the 10,000, 7x plus y greater than or equal 200, 4x plus 2y greater than or equal 140, and 2x plus 4y greater than or equal 100. Okay. Okay. Then let's graph the constraints. Step 4. Graph the constraints and identify the feasible region, right? Also, we wanted to add two constraints, non-negativity, x greater than 0, y greater than 0 here. First one, 7x plus y greater than equal to 100. Second, 4x plus 2y greater than or equal 140. Third, 2x plus 4y greater than or equal 100, and x greater than 0, y greater than 0. So let's define when x equals 0, y equals 200. When y equals 0, 7x equals 200, then x equals 200 divided by 7. 200 divided by 7, that is 0.57. Here when x equals 0, 2y equals 140, then y equals 70. When y equals 0, 4x equals 140, x equals 35. So the points here, then when x equals 0, 4y equals 100, y equals 25. When y equals 0, 2x equals 100, x equals 50. Also from here, x equals 0, y equals 0. Okay, let's get the points. 0, 200, and 200 over 7, 0, 0, 70, 35, 0, 0, 25, 50, 0. Okay, then let's draw the graph. Axis, y-axis. So we have 0, 10, 20, 30, 40, 50, 60, 70, 80, 10, 20, 30, 40, 50, 60, 70, 80. So negative 10, negative 20, negative 10, negative 20. It's up to you to use the appropriate measurements, right? Okay, first 0, 200. Oh, sorry. So we wanted to use a large scale, right? 0, 0. Let's use 50, 100, 150, 200, 250. Y-axis. For this way, 20, 40, 60, 80, 100. Okay, 0, 200 and 200 over 7 and 0. Okay, again a solid line, okay, like this. So this is the line. 7x plus y equals 200. Okay, and the region, when we put the 0, it doesn't count the value greater than 0, greater than 200. So above the line, because greater than, above the line, the feasible region above the line for the given constraint. Let's draw the second one. 0, 70, 0, 70 and 35, 0. Again a solid line, and that is the line 4x plus 2y equals 140. Also the region above the drawn line. Next, 2x plus 4y equals 0, 0, 25 and 50, 0. 50, 0. That is the line 2x plus 4y equals 100, again above. Right? And x greater than 0, y greater than 0. So x greater than 0, that way. Y greater than 0, x-axis and above the axis. Okay, it's hard to find the feasible region, but we wanted to find it out. So let's find the feasible region. So the feasible region would be or this overlapping region which satisfied all 5 inequalities. So above this, definitely above this, this. So, okay, it's hard to find then. Okay, let's go again. Okay, unbounded region right above here. Okay, what are the corner points then? So the corner points are this, 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 this. 4 corner points, right? Okay, let's find the corner points. So 0, 200. And this point we don't know. We wanted to find the intersection of that black and purple lines. The black line is 7x plus y equals 200. Purple line is 4x plus 2y equals 140. And this we don't know the intersection. That is the intersection of purple and green lines. The purple line is 4x plus 2y equals 140. And the green line here is 2x plus 4y equals 100. And the fourth one, we know that here we have 50 and 0. Those are the 4 corner points. Then let's find the corner points. The first one here. So we wanted to find the 2 intersections, this one and this. Okay, let's start with this intersection. Seven x plus y equals 200. 4x plus 2y equals 140. So easy to multiply the 1 by 2 minus 2. 2 times 7x plus y minus 4x plus 2y. 2 times 200 minus 140. 14x plus 2y minus 4x minus 2y. 400 minus 140. So 10x equals 400 minus 140, 260. So x equals 26. And 7x plus y equals 200. Then y equals 200 minus 7x. Then y equals 200 minus 7 times 26. 7 times 26 is 182. Then y should be 18. The first intersection point here, that one, should be x equals 26 and y equals 18. Okay, let's find the second intersection point. Intersection of purple and green lines. So 4x plus 2y equals 140. And 2x plus 4y equals 100. 1, 2. Easy to do that. So 1 minus 2 times 2, 4x plus 2y minus 2 times 2x plus 4y. So 140 minus 2 times 100. 4x plus 2y minus 4x minus 8y equals 140 minus 200. So negative 6y equals negative 80, no, negative 60. So y equals 10. Then by substituting y, 2x plus 4 times 10 equals 100. 2x plus 40 equals 100. Then 2x equals 60. X equals 30. So the second intersection point here, x equals 30 and y equals 10. Okay, so 26, 18, this is 30, 10. So we know all four corner points. We know all four corner points. Then evaluate step 5, evaluate the objective function. So the objective function was cost function 1000x plus 800y. Then corner points, cost. The corner points were 0, 200, 0, 200, and 26, 18, 30, 10, and 50, 0. Okay, let's evaluate then. Z equals 1000 times 0 plus 800 times 200. So 16,000. Z equals 1000 times 26 plus 800 times 18. $40,400. Z equals 1000 times 30 plus 800 times 10. $38,000. And Z equals 1000 times 50 plus 800 times 0, 50,000. So the minimum cost, not the highest one, because we are going to minimize the cost. So the minimum cost is at the corner point 0 and 200, 16,000. Therefore, the minimum cost is 16,000. 0 adds in the newspaper 1 and 200 adds in newspaper 2. Okay, I hope everything clear so far. Then you can practice these 2 exercises. Here are 2 exercises. Practice it by your own to get more practice. And think about the common mistakes. The biggest mistakes in linear programming problems are forgetting non-negativity constraints, using the wrong inequality sign, and evaluating the objective function at points that are not corner points, and forgetting to graph all constraints before identify the feasible region. So would like to go through it. So keep this in your mind. So don't do the common mistakes again and again. Okay. So let's summarize today's lesson. Today we learned how to solve linear programming problems using a systematic approach. We learned how to define decision variables, write an objective function, translate word problems into constraints, graph the feasible region, identify the corner points, and evaluate the objective function to find the optimal solution. So in the next lecture, we will continue solving more complex linear programming problems and learn additional techniques for finding optimal solutions. Thank you for watching, and I'll see you in the next lecture.